pleased to introduce to you today Junellie Gonzalez Quiles, who's currently pursuing her PhD at the Johns Hopkins University. And she's been there for quite some time. Actually, she's done her bachelor's there on magnesium oxide. So she's obviously been involved with high pressure and high temperature characteristics, which is very relevant also to the field that she's going to talk to us today. She's also originally from Puerto Rico, which is very interesting because that is where the big radio telescope was decommissioned just some time ago, and she was mentioned in this regard. So, Junellie, we are very excited today to have you. So you've already gone one step ahead. You're already sharing your screen. So I'm going to hand over to you. By the way, Junellie's got 6 questions for us. You break all the records, all the exoplanet records. So just tell me when you want to launch these questions.
Perfect.
And, yeah, okay, I'm going to be quiet now. Okay, there you go.
Thank you so much for that lovely introduction, and thank you all for your patience in me getting here. I'm very honored to speak with you all today about some of the greatest breakthroughs of the exoplanet field, but also things that I've been focusing on and working on throughout my bachelor's and my graduate degree. As Dr. Sase mentioned, I am originally from Puerto Rico, and I actually fell in love with space at the Arecibo Observatory, which is unfortunately not working anymore and has been decommissioned. But I am very grateful that I had the opportunity to get into this field and now working on this exciting research. So before I begin talking about other planets and then talking about geology of distant planets, I just wanted to start by looking at this image. So I know, especially myself, when I was a kid, I would gaze at the stars in the mountains of Puerto Rico, and I would always ponder whether are we alone in the universe and whether life could exist elsewhere. And I'm sure that many of you actually here have probably at some point or another asked ourselves this question. And so this is one of humanity's biggest questions, right? We want to know if there is life in other planets. And so in my quest to answer this super huge question, I landed here at Johns Hopkins, where I study exoplanets. And you may have heard this concept before, but just before I talk about it more, I just wanted to define it. So exoplanets are planets outside of our solar system. So essentially, these planets are orbiting, going around other stars that are not our sun. And so this is huge because only a couple decades ago, we thought that there could be other planets, but we hadn't confirmed any exoplanets outside of our solar system. And so that has been a huge breakthrough in the last couple of decades, really. It has launched this huge field of exoplanets. And that's why I'm studying today what I'm studying. And so I want to launch the first question, which is, how many exoplanets do you think we've discovered so far? Please feel free to answer. Truthfully, we're all here to learn, and I'm happy to share with you. So yes, please take a couple of seconds, answer that, and we'll reveal the results in a bit.
So this is going to be exciting because, I mean, maybe the question, just like you said, how many have we discovered? That's important because it's in the question, it says, how many are there? Well, we don't really know how many there are. I can say that with absolute certainty.
Yeah.
So yes, how many have we discovered?
Yes. So I don't know if you can share the results.
Yes, I will. I just usually leave it for 1 minute, Junellie. Okay.
That sounds perfect.
So give them a few more seconds, and then I will share the results,
problem.
and then you can comment on them. Okay.
Awesome. Yeah, just let me know, and then we'll go. But yeah.
Okay. What do you think?
Yes, awesome. So a couple of you mentioned 10 to 100, some 100 to 500. Some 500 to 1,000, but the most consensus was between 1,000 and 5,000 and 5,000 or more. And so actually, I'm going to progress my next slide. There's more than 5,000 exoplanets discovered so far, and many more are in queue to be confirmed exoplanets, which is extremely, extremely exciting. And so thinking about that huge number, again, only a few decades ago, we had not confirmed any planet outside of our solar system. We only knew of the planets in our solar system. And so when you think of a planet, you may think of these images of Earth, Mars, or Venus. And so let's see. Sorry, I'm trying to. Okay. So when you think of these planets, you think of these images that we've gotten from NASA, from spacecraft, and we see the rich, exquisite detail that we get from the surface, from the atmosphere of these planets. And so this is really exciting. And so when we think about our solar system, so these are some of the terrestrial planets in our solar system that are closer into our sun. So here we have Mercury, Venus, Earth, and Mars, which we see are much smaller compared to the outer four planets, Jupiter, Saturn, Uranus, and Neptune. And so the big difference here is that these outer planets, Jupiter, Saturn, they're more gas giants. They have thick atmospheres dominated by hydrogen and helium, and Uranus and Neptune as well, but they're more ice giants. And then we have the smaller rocky worlds in the interior of the solar system where our planet Earth is, and we know there's life in it. And so I just want to ask a question about whether you think that we could actually see this detail. Can we get images like these planets for exoplanets? So now thinking about planets outside of our solar system, can we get these images? So please feel free to answer truthfully, and we'll go over it in a second.
Okay.
Amazing. Okay, so a couple of you said, yes, we can. We've seen them already. Some are not sure. Maybe we do. And most of the attendees here think that no, we cannot get similar images for exoplanets. And you probably remember the picture that I had as my introductory slide, and you probably think that's an actual image of an exoplanet. And so one big thing that I want to let you all know is that no, we cannot get this rich detail on exoplanets. And so one of the biggest things is that if we want to take an image of a planet, of an exoplanet specifically, this is as best as we get. So this is a direct image of the system HR 8799. It has 4 planets around it. And so this is as best as we get as an image for it. So as you can see, we cannot resolve the features on the planet. We cannot resolve like any atmospheric features as well. We cannot look at the surface. And so then astronomers, the best thing that we can do right now is be able to get the gases or what kind of molecules make up the atmospheres of these planets. So that's as best as we can do right now with current technology, with current missions. The best thing that we can get right now is what kind of molecules make up the atmosphere. And so as we see, astronomers have been pushing the boundaries with these space telescopes, to be able to even detect these molecules in distant planets. And so in our search for life, that is a huge question. Can we use what molecules we find on the atmosphere to say whether there is life or not? That's where it gets a little bit complicated. And so right now we're only observing at the current age of the system what kind of gases are present, but that's it. So there's a lot still to learn about exoplanets, which is pretty exciting. And so I just wanted to talk briefly about what kind of methods astronomers use to be able to detect these exoplanets. So as I shown here, one of them is direct imaging, literally looking at the star, blocking the star as we see here, and then being able to resolve the planets around it. But the other technique is called the transit technique. And as you'll see here, this method consists of when the planet passes in front of the star, it blocks part of the starlight that we receive. So as you can see here on the left bottom, it shows the light, the amount of light that we get over time. And so as the planet passes in front of the star, it blocks part of that light. And that's how astronomers can confirm that there's a planet present. But this is just one of many techniques that exist, but this has been proven one of the most effective techniques for detecting and confirming exoplanets. And so now I just briefly want to talk about and bring you back to our solar system. So we see that we have planets, terrestrial planets, we have gas giants, and we have ice giants. And so when we look at exoplanets, we then follow a similar framework, and we think of different types of exoplanets. So here's a brief sketch that talks about the different exoplanet types that astronomers have been able to detect so far. So one of them is terrestrial, similar in size to Earth and Venus. And so there's also Neptune-like, kind of like Neptune, as the name suggests, as an ice giant. There's also gas giants, also known as similar in size to Saturn or Jupiter. But then there's this interesting type of exoplanet that is not present in our solar system, which is called the super Earth. And as you can imagine from that name, super Earths are terrestrial bodies such as Earth, but bigger than Earth. And so this type of planet has actually been seen quite often around other stars, but we don't have any analogs in our solar system to be able to compare them to exoplanets. So this is like really exciting. We're definitely looking and finding these other types of worlds that we've never seen and pushing the boundaries of what we know about planets overall. And so now I want to talk about bringing you back to the transit method. So let's take here. So here you see that blue dot as an example of what Earth would look like around a sun-like star, right? So we see a star like our sun on the left. And so the transit technique is going to look for these planets around these stars. And so if you didn't know, there's also different types of stars. So there's also these stars called M dwarfs. And so M dwarfs are smaller, redder stars. As you can see here, this is not to scale, but this is just to show they're smaller than our sun. And so this is really interesting. And so I just want to ask the next question, which is, if you had a planet like that blue dot around each one of these stars, which one would produce a bigger signal for us to be able to detect it?
Yep, that is a great question. Here we go. Share results. Let's see what you say.
Awesome.
Isn't it?
So a couple of you said that the bigger star like our sun will help produce a bigger signal to be able to detect it, while most of you answered that the smaller star, M dwarf, will produce the bigger signal. And that is actually what happens. So if you think of the planet passing in front of the star, it blocks a bigger portion, a bigger area of the star. So if the star is smaller, then we actually get a bigger signal if you take the same planet size around both stars. And that's because the bigger, the smaller the star, the bigger the area the planet would cover of the star. If you have any questions about this and you would like me to clarify, please feel free to ask questions, and I can definitely answer that as well. And so my next question is, then now, if we have the same star, what planet would produce a bigger signal to be able to detect it. So now, keeping the star size the same, what kind of planet will produce a better signal to detect it? A planet like Jupiter or a planet like Earth?
Okay, there you go.
Awesome. Okay, so most of you said the bigger planet will produce the bigger dip, and some of you said not sure. So I will play this video now, and we will see that the bigger planet indeed will produce the bigger dip. And so that means that bigger planets around, if you kept the star size the same, will produce a bigger dip, a better chance at detecting these planets. And so that's why I didn't mention before, but planets that are big like Jupiter-like planets that have been discovered so far, gas giants around exoplanets, most of them have actually been found super close to their star, also called hot Jupiters. And so that's another type of planet that we don't have in our solar system, right? Jupiter is far from our sun compared to a hot Jupiter, which is extremely close to the stars, closer than actually Mercury is to our sun, which is pretty wild when you think about it. And so there's a lot that we're definitely learning about exoplanets and how they can evolve and form around these stars. Okay, great. So I just also want to chat about, I know I mentioned that right now astronomers we can detect the molecules that make up their atmospheres, but how exactly do we do this? So here, take that we are on Earth, right? We're observing a star and we see a planet transit in front of the star. So if the planet had an atmosphere, some of that starlight that we would see on Earth would actually pass first through the exoplanet atmosphere, and then get to us. And we can actually observe this light that we get from the star and passes through the atmosphere, and we can break it down into different colors. So think of a prism. You can break the light into different colors. And so using this similar technique, you can actually see what molecules make up the atmospheres of these exoplanets. So that's how exactly astronomers study these specific planets, which is pretty exciting. And so I've hinted at it before, but the James Webb Space Telescope was launched Christmas Day, December 25th, 2022. I woke up early, not for Santa, but for watching this launch. And so it launched then, and it has completely exceeded everyone's expectations. We've started using the 6.5 meter telescope to be able to look at small planets around nearby small stars, kind of like M dwarfs, as I mentioned before, right? Because the smaller the star, the better the signal is. So James Webb has been looking at these other stars and looking at terrestrial planets around them. So actually having a smaller stars favor our study of smaller bodies. And so that's really exciting because we've been using JWST to then finally start hopefully answering this big question of whether there is life and what kind of molecules make up their atmosphere. And so I know you've seen a lot of these news out there about all of the exciting results that have been coming out about from JWST, which is amazing and super exciting. And as you can imagine, JWST has a specific lifetime that it will work for. And so, as I mentioned at the beginning, there's over 5,000 exoplanets. So that means we got to prioritize what kind of planets we're going to look at. And so the TRAPPIST-1 system is one of the systems that JWST has been looking. And before I go on, I wanted to ask, how many of you have heard of the TRAPPIST-1 system? Awesome. thank you all for sharing in the chat whether you've heard about this system. So this system was discovered very recently. Actually 2016, 2017, all 7 of these planets. So this is a system that has 7 terrestrial planets around an M-dwarf star. And so this is extremely exciting because then that provides a natural laboratory for us to study the habitability of terrestrial exoplanets like Earth. So that's extremely exciting for us to study. And so when we're also thinking about habitability, you've probably also heard about the concept of the habitable zone. And so I'm going to talk briefly about what the habitable zone is. So the habitable zone is a concept that astronomers came up with to be able to describe the Goldilocks zone, the region around a star where liquid water could be present on the surface of the planet. And so as shown here in the image, the green area is the just right. The red is too hot and the blue is too cold. So ideally, we want to look at these planets that are in the just right zone, right? When we're looking for habitability. And so this is something really exciting that we're starting to look at. So I know that actually a couple of my colleagues have already received the data about these planets to be able to learn what kind of gases make up their atmospheres if they have atmospheres. And so very soon, hopefully, in the near future, we'll be able to know whether these planets have atmospheres. And if they do, how similar are they to Earth? And so this is extremely exciting. But again, we are only limited to learning exactly what kind of gases make up their atmosphere. And so I'm going to use an analogy here to drive this point home. So imagine that you're in a bookstore and you're browsing for books. A book catches your eye, so you look at the cover. But after reading the description, you decide it doesn't look interesting to you, so you put it back, right? You then later wonder if you might have missed the opportunity to read a good story. Now, what if I told you studying exoplanets is just like choosing and reading books? Astronomers, as I mentioned before, can detect the atmospheres of these exoplanets. But unless we look within, we might miss important clues for finding life. So this is where my research comes in. I am extremely interested to learn how the interior of planet, what all of that makes up the interior of a planet, can influence the atmosphere that we see today. But you may be asking yourself, how can we look deep into these planets if we can barely look at the surface, right? So just like there are volcanoes on Earth, which spew large quantities of water vapor and carbon dioxide into our atmosphere, other exoplanets may experience the same. So by studying the geological processes that happen deep inside the planet that lead to the generation of these gases, we can then understand the molecules that make up their atmospheres and maybe predict what we can see today with telescopes. So I just want to show here, this is a video taken from a satellite on Earth.
Junellie, do you want me to launch your poll in this regard, or?
Yes,
Yeah,
please
okay,
do.
I'll do that right now. Okay, so yeah.
Thank you. So the next question is, could we see volcanoes and or plate tectonics on other planets?
I think this is a very interesting question.
Yeah.
I think there are very divided ideas here, so it'll be interesting. I would give it
Okay.
Uh-huh.
Yeah. So pretty split. So 30% of you said yes, we can. 50% said no, and a couple of you were not sure. So this is something that I will address in my next couple of slides. And so right now, we are not able to see volcanoes and or plate tectonics on exoplanets. However, we have seen some cryovolcanism on moons around planets in our solar system. So while not on exoplanets, we cannot see volcanoes and or plate tectonics on exoplanets, we do have other examples of these kind of processes happen in our solar system other than planet Earth. So here in this slide is an image of Earth. So it's a satellite image. And we can see a volcanic eruption. This was the Hungatonga volcano that erupted very recently, actually. And so as you can see, as I mentioned before, we see a lot of carbon dioxide. This actually put a lot of carbon dioxide and water vapor into our atmosphere. And so with this process, you can very visibly see how geological processes can directly impact the atmospheres that these planets have. So I want to go a little bit in depth now, as time allows. Why are these processes happening here on Earth? And so you may have heard of this concept, plate tectonics, right? Like I mentioned, I asked about it in the question. And so this is an image of the different plates that our surface of Earth are composed of. So actually, this area right here, this boundary between these plates, you can actually see if you go to a satellite image on Google Maps, you can actually see this, which is pretty cool. And so to bring it to home, exactly how we see plate tectonics in our everyday life, earthquakes happen, right? And this is due to plate tectonics. And so I'm going to briefly talk about the different type of plate boundaries and how specifically how plates can interact with each other. So you can imagine that if we have two plates moving away from each other, so that's called a divergent boundary on the left-hand side here, you can actually have material come up. And that's how in the bottom of the ocean, more oceanic surface is basically formed. So, now imagine if you had two plate tectonics moving towards each other. So they will clash, right? And that's how also a lot of earthquakes happen, right? There's a lot of pressure in between them. And eventually one of them gives out and goes into the inside of Earth, of the mantle. And finally, the transfer boundary essentially means that they're just passing each other. They're not interacting specifically, but they're just passing against each other. So why are plate tectonics so important on Earth? So as I mentioned before, Earth has plate tectonics, and actually currently it is the only planet and moon and like body in the solar system and outside our solar system that we have confirmed that has plate tectonics. So we only have Earth as an example. And so plate tectonics is crucial for driving important geological processes such as the carbon cycle. And the carbon cycle is very important because over long geological timescales, it helps regulate the temperature of Earth, which is extremely important for us for habitability, right? We don't want a really hot planet like Venus, where it has so much carbon dioxide. It's just a hot world, and like humans, and there's no like, as far as we know, there's no life that we've been able to find in that environment. And so I'm just gonna quickly go through exactly how the carbon cycle works. So imagine here that we have water raining down, right? That water interacts chemically with the rocks on the surface. And so the more carbon dioxide that you have in your atmosphere, the hotter it can be. And so that actually makes that chemical reaction speed up and basically be more efficient. And so through that process of chemical reactions, you actually get carbon taking out from the atmosphere, from that CO2 that's in the atmosphere, and put into that water that's reacting. And so you can imagine that water then goes down to the bottom of the ocean or down the rivers. And it also happens at the bottom of the oceanic floor or seafloor. You can imagine then that carbon, that water, can then be put into the interior of a planet, into the mantle of a planet, by subduction, a process called subduction. And all that means is that if you recall again the plate boundaries, two plates moving against each other, one goes under the other plate. And that's how you actually get carbon from the atmosphere to the surface to the interior. And finally, as we saw from that video of the volcano, we get that carbon out back again into the surface and atmosphere in a process called outgassing in the literature. But all that means is that you have volcanoes that spew gases into the atmosphere. And so how exactly do I study these processes on these exoplanets, you may be wondering. So I use models. And when I mean models, I mean a set of equations that describe theoretically each geological process over time in a computer. So I basically take these equations and then I put in different planet properties like the mass, the radius, so how big the planet is or how small it is, how massive it is, how small it is, the estimated age of the exoplanet. And so this is the amount of time that I will run that model for. So essentially what I'm doing is taking the planet after formation and then putting all of these basically variables in, and then just letting it run using the equations that we know for geological processes. I also take into account the initial water and carbon that a planet may have. So you can imagine that different stars will have different amounts of molecules that go into creating these planets. I then run these models, which then gives us the amounts of these gases that would make up their atmospheres. So just to remind you, right now, current technology is we're limited into knowing what gases make up their atmosphere. That's as much as we can get. So my goal through this kind of research is to be able to use our geological understanding of these planets and see if we can use that to predict what we would expect to see in the atmospheres of these exoplanets. So I know that was a lot, so please feel free to ask questions if you have questions about this. But essentially what we want to do is use this geological framework and ask ourselves, can we say something about how the planet evolved over time using the geological activity that could potentially happen if you had plate tectonics? And so this is something that I'm really interested in, and this is where we're pushing the boundaries, right? Like there's upcoming space missions that are happening, space telescopes that are going to be launched. And ideally, we want to answer the question eventually, of are we alone? And so just to recap today, were you able to learn today? I hope that you were able to learn something today. We went over what are exoplanets, what different types of exoplanets there are, how are they detected, what are plate tectonics, why are they important on Earth and on other planets potentially, and how it helps drive geological processes like the carbon cycle. And I explained briefly how we use those models to try to predict what gases will make up the atmospheres of these exoplanets when we observe them with telescopes. So I just want to finish off my talk here by saying that I know a lot of you know this saying, don't judge a book by its cover, right? So I would say don't judge an exoplanet by its atmosphere. We need to look inside an exoplanet to be able to understand the full story of an exoplanet, right? We want to be able to know if there could be life in these other worlds. And if we judge an exoplanet by its atmosphere, but we completely disregard the geological evolution and basically its full story, then we might be missing important clues for finding life. And so this all comes down to being able to answer the huge question, are we alone in the universe? So thank you so much for, again, for your patience for me to get here. And I hope you were able to learn something, and I'm happy to take any questions now.